Okay, so for this one we need to determine the difference between a linear equation and an exponential. And what we're going to be deciding on the types of behavior is if it's increasing or decreasing, and then of course which kind it is. So linear equations take the form of, let's go a little bit thicker, y equals mx plus b. And the deciding factor on increasing or decreasing is the slope, the number in front of the x. If the slope is positive, we have increasing. And if the slope is negative, we have a decreasing. Okay, so going down, going up. Okay, increasing. For exponentials, what we have, so I'll label that linear. For exponentials, what we have is an equation y equals a times b raised to the x. So the variable is up in an exponent. That's how we kind of tell that it's exponential. Now there's kind of two ways to decide whether it's increasing or decreasing. The base, if it's larger than 1, it'll be decreasing. Or sorry, larger than 1 means bigger than 100%, which means we're getting more. This is our increasing exponential. And they go like this, going up. If b is less than 1, so that's less than 100%, we're losing some, and so that means we're decreasing. And those type of exponentials kind of go down like this, so they're decreasing this way. Those are the quickest way to take a look at what we're doing. So this first one, there's no exponent. G of x equals negative 16x, so this is definitely linear. And the slope is negative 16, so that is a negative slope, so it's decreasing. The second equation, f of x, this is definitely linear. Again, there is no exponent, so it's linear. And this one has a positive coefficient, so it's going to be increasing. It's going upwards. D of y, there's an exponential up here, so that is an exponential. There's an exponent. The base is larger than 1. 3 is bigger than 1, so that has to be increasing. T of t, we also got an exponential. We see an exponent. T is an exponent, so that's exponential. And the base, 1.25, also is larger than 1, so that's going to be increasing. H of x, we've got exponential. There's the variables up there in the exponent. And the base is 0.7, so that is less than 1. That's a decreasing exponential. Just like that. Okay, 24. So now we're given an exponential function, and I just look at that first before I look at too much, and I see there's a variable t, that's the exponent, and then there's an output v of t. So what do they mean? Well, t is years. So I just read that. T is the number of years. And it represents, this equation represents the value in dollars, so that's why V is you know, it's going to be dollars. That the value of whatever we're talking about. Of a car, I guess we're talking about a car after it's purchased. Use this function to complete the statements below. The value of the car is blank or blank. Either, again, we could click on that. We'll see it's going to be probably increasing or decreasing at a rate of blank. Purchase price of the car was so much. Okay, so remember, when we have an exponential, we have to talk a little bit about these, which is what we have. That the a is our initial value. Initial value. The b, we subtract it. So if we take b minus 1, that's going to give us the rate. Okay, so whatever b is, b minus 1 will be the rate. So the value of the car is increasing or decreasing. Just like last time, the rate is less than 1. It's going to actually be a negative rate when we get it, but it's less than 1, so it's decreasing. And what is the rate of decrease? Well, we take our 0.94, subtract 1, and what we get is that it's decreasing. It's a negative rate, right? When you plug this in your calculator, you're going to get 0.06. Or, as we would say, it's a 6% decrease. And that's going to be percent per mile. It's going to just be 6%, but it's percent per year because that's how it's measured, right? Percent per year. So we'll put in our 6% per year. So 0.06. Notice I didn't put the negative because the negative is right here. It says we're decreasing. So that takes the place of the negative. The purchase price of the car was blank. So that's the initial value, and that's going to be in dollars, $23,500. So that's the number that's in front. That's our initial value. That's our y-intercept, our vertical intercept. Okay, so that's all you need to know about exponential functions is the number in front without the exponent. That's going to be your initial value, the starting value, the vertical intercept. And then we can get the rate by the number that has the exponent on it. That's very good. Question 25. So we have some change functions or some different ways of changes going. Now, again, linear is an amount of change. Exponential is a percent change. So that's how you can tell the difference between there. And then we can come up with our equation from those previous one. And again, remember, linear is going to be y equals mx plus b, where m is our rate and b is our starting value. So that's going to be linear, and then percent change or exponential will be starting value, which we label A, times the base, which is going to be 1 plus the rate. And again, if we're losing, it could be a negative rate, so it'll subtract. And we'll do the rate as a decimal, and then we've got some variable up here. Okay, so first of all, we know it opened in 1980, and there were 920. So there's our initial value. Initial. And then we're going to write a formula. So if we're increasing by 61 students per year, that's an amount of change. That's our slope, 61 every year. So we're going to put in 61 times the variable, which in this case is t rather than x, plus what we started with, 920. The B question decreases by 70 students per year. It's going to be a similar type thing, but the rate is decreasing, so that's negative. 70 students every year, that's t, plus 920. That's our initial value. Now we get into the an exponential one. It's decreasing by 14%. And that one takes a little bit more thought. But 14%, remember, so to get our rate, or to get our base, we're going to take 1 minus the rate, 14%. So we're decreasing by 14%. That's going to be 0.86. Okay. And so remember our format for exponentials. We're going to have n of t equals the starting value, 920, times the base, 0.86, and then that's going to be raised to the t power. And again, you can use a little yellow arrow here if you want to, but we'll just do it this way. So that's, and again, what it allows you to do is it looks exactly as it should when you input it. Remains constant, so if something doesn't change, well, we have 920 students, and we have 920 students every year. That's the constant function. It actually fits with the linear. What you could think of it, it's 920 plus 0t. There is no change. Then we're increasing by 13%. And again, for this one, we just find our base is going to be 1 plus 0.13 because we're increasing. So this will be 1.13. Oops. Well, let's go ahead and use the little yellow up arrow here, and we'll put in, again, it's always 920 because that's what we started with. Our base is 1.13, and that needs to be raised to the t power. And we'll check our inputs. What did I mess up here? Let's see. 14%, 1 minus 14. Oh, there's a comma. I think I did that. That should be a decimal. Oh, it's a comma. That's the decimal. Okay. Let's try that one again. So the answer was correct, but I put it in wrong. My formatting was wrong. So look at 26. Okay. And again, we're seeing we're into the exponentials here because we're dealing with a percent. So I just start looking at numbers before I do too much reading. Okay. Okay, house purchase for $155,900 gains 3% of its value every year, so consistently. If this growth rate continues, in how many years will it be worth twice its original value? So we know we started with, so our equation is always y equals a b to the x, and remember b is going to be always 1 plus the rate. The rate is 0.03. So our base is 1.03. So our equation is going to be the starting value and then it's going to be 1.03 to the x or to the t if you want. I like to use x if I get the choice. And then we want to know when will this, when will it be twice its original value? Okay, so we're going to need to solve for x. So what's the twice the original value would be twice what we started with. So we take 2 times 155. So that's the original value. We want to know when the house will double. So when is it worth $311,900? 311,900. That's what we're looking for. Now, another way we can use Desmos is we can graph both sides of this equation. So what we're going to do is we're going to graph this side as y equals 311,900. We'll graph this side as y equals that equation, this equation up here. And where these two intersect, that will be our answer. Okay, so it's a great way to use the graphing capability, Desmos. So come back to Desmos. I have to enter both of these, so I'm just going to go y equals 311,900. And down here I'm going to go y equals, just clear it out, y equals 155,950, 1.03 raised to the x. Okay, and notice I don't see much, but notice my numbers are pretty big. Y is equal to 311,000. We're only at 600. So what I'm going to do, like that, we have to zoom out, right? Quite a bit. There we go. We see that. And there it is. We see that. We've also zoomed out into the x values, but notice all we have to do is click here, and it will give us our answer, where the intersection is between the y equals 311,000 and the exponential, which is looking like a right-angled curve, but that's because the time has come out, is 23.45. That's when it'll be doubled, 23.45. I'm going to write that down here. And that's what x is equal to, 23.45. Make that again. Oops. That's the y-intercept. That's the problem. There we go. That's the one we want. 23.45. Okay. And round your answer to the nearest tenth as needed. So we'll do that 23.5. And your answer to the nearest tenth is needed. See if it just doesn't round it. That's strange. They didn't round it. Round your answer to the nearest tenth as needed. So we'll have to watch out for that. It really, rounded answer would be 23.5. But good thing we checked, right? So I do check over those. But you can use that method. So let's look at 27. Again, another exponential. So now this time we've got a fox population growing at 4%. We've got a starting year of 2000. That's where 14,700. Estimate the fox population in the year 2008. So 2000 to 2008, that's 8 years, right? 2008 minus the starting year of 2000. That's going to be 8 years. Our equation, 4%. So you get that our base is equal to 1 plus the rate. So that's 1 plus 0.04. That's the amount that it's increasing by. 1.04. And then our starting was 14,700 times our base raised to the number of years. So this is going to be our population. And what we're told is that the number of years is 8, so we'll just plug in 8 here. We can do this with a scientific calculator or any calculator that has a exponent key, and this one does. So let me clear it out. 14,700 times 1.04, and I use this x to the y, and that's 8 years. So notice it's right here to the 8th power. So after 8 years, we should have 20,117. Probably want to round it to the nearest box, so we would round up, and we'll enter that as 20,118. And hopefully Moore has done a correct, oops, I didn't want to do that. At least I got my answer here. 20,118. And there we are. We're good. We didn't have to use decimals that time. Okay. This next one. After graduating from college, Carlos receives 2 different job offers. Both pay a starting salary of $50,000. One promises $2,000 a year raise, which again, that's going to be linear. That's an amount of change, while the other is a 4%. That's going to be exponential because it's a percent. Okay, so this is linear. This is exponential. Complete the table below. So for 1, 5, and 10, this is with the 2,000 raise. So again, it's going to be a linear equation. The salary starts at 50,000, and each year we're going to add 2,000. Here we go, 2,000 x, and x will be our years. For the exponential, it's going to look similar. We start with 50,000, but what we're adding is a 4%, that's 0.04, so that's 1.04 each year to the x. And again, we'll calculate it at 1, 5, 10, and that's it. So the first one, we could plug in 1, so 50,000 plus 2,000. This is really at the end of the first year. Carlos will be receiving 52,000. After 5 years, well, let's look at this calculation, would be 5 times 2,000. 5 times 2,000 is 10. 10,000. 10,000 plus 50,000 is 60,000. And finally, after 10 years, 10 times 2,000 is 20,000. 20,000 plus 50,000, that's 70,000. Again, you could use your calculator on these, whatever you need to do, but what we're doing is we're just plugging in these values for x into this equation. We'll do the same thing here, but we're going to use our calculator because I'm not as good as calculating 1.04 to the 5th power in my head. So we just need a standard calculator. or a scientific calculator. Clear what we have. For the first year, well, it's not. We'll still use it. So 50,000 times 1.04 raised to the 1 power 52. So we're equal there. So no real difference after the first year. But let's see what happens after 5 years. Do the same thing. We've got 50,000 times 1.04 raised this time to the 5th power. That's 60,832. And how they want it rounded to the nearest dollar, we'll round that to 33 because the 6 rounds up to the 2. So 60,833. And then finally, so we're ahead by 5 years by $800. So that would be the better deal. And let's see, after 10 years, what's going to be the deal? 50,000 times 1.04, again raised to the 10. 74,012. No, we round down. 74,012. So 4,000 ahead. And we're all correct. Okay, 2 more and we'll take a little break. Okay, now this is specifically an exponential. We're not having to deal with linears. So we've got this right up here. So we want to select all the things we know about it. So certainly, is this growing or decaying? Well, this number here, the base is less than 1. So we know it's decreasing. Okay, it's going to be decreasing. Again, you could actually graph this and see that. Growth or decay rate. Remember, to get that, we need to take 1 minus 80, or 100 minus 81%, however you want to do it. That's kind of how I can think of it. It's going to be a 19% decrease. And say they want it as a percent. There's a percent here. So we want to, it comes out as 0.19, which is, negative 0.19, which is a 19% decrease. And again, they've got the word, we're already saying it's decay, so that's where the negative comes in. We just put in 19. Now, what's the domain? The domain, well, we can plug anything in for x. We can even plug in negative numbers to kind of figure out, I don't know what that would mean, but our interval, I would use this. We go from, they don't give us too much to do, but we go from negative infinity to positive infinity, and we put parentheses around that. That's our interval. Now our range, remember our range is for all exponentials, the output is, this is always going to be bigger than 0. Even though it's going to decrease, remember exponentials, the graph will look something like this, where it's going down, down, down. So that's an exponential function. It's getting close to 0. It'll never equal 0. And then it goes up to infinity. So that's the range of an exponential function. So we go from the smallest value, which is 0. So 0 is not included, but that's as low as it's going to get. And then it'll go, the y values go all the way up to infinity. Okay. Vertical intercept, well, that's the starting value, right? That's 500. They want it as an ordered pair, so when x is 0, when x is 0, y is 500. Horizontal intercept, it doesn't exist. Remember, exponentials get closer and closer, but they're never going to touch that x-axis. They're never going to cross that x-axis. That is a D in E. So that's how we do that one. One more, we'll take a little break, and then we'll move on. So properties of exponents, and hopefully on this one, n to the 0 power, that's always going to be 1. So maybe we put that in. And again, you could check this out on your calculator. Any number raised to the 0, except for 0 itself, is going to be equal to 1. 0 to any power, except 0, and because they say they're non-zero real numbers, is actually always going to be 0. It doesn't, because 0 times 0 is still 0. Now, some number to the first power, what's that going to equal? It's going to equal itself. Whatever n is, everything is sort of listed as to the first power. Okay. 1 to the n power, again, 1 times 1 times 1, no matter how many times you multiply, it's always going to be 1. It's always, okay. And then with the negative exponent, this is going to be whatever n is. If you take it to the negative 1 power, that's the reciprocal. So that's 1 divided by n. There we go. And as long as, because we're told that the variable is a non-zero real number, this is always going to be okay, because as long as n is not equal to 0. So those are the properties of exponents. In the test, you will obviously be requested to understand these properties as you solve other questions. Okay, so we'll take a little break here and then move forward.